embedding of two spaces that you were telling.
Yes.
So I didn't get that idea.
Yeah, you had that question. Embedding of two spaces. So what was the question about it?
You were discussing regular spaces.
Yes.
So we have the region in the positive x kind of.
Yes.
And you said that it's also possible in the negative x and it's equivalent embedding of.
Yeah. It's not embedding. It's this thing. It's a doubling of the space actually. Okay, let me explain that. The question is, last time we saw that Rindler space, which has a certain metric, is equivalent to flat Minkowski space. We just did it in 2 dimensions for simplicity, but the story goes through in any dimension basically. And what we found was that Rindler space was giving us, when we map back to, when we change coordinates back to Minkowski space, we find the positive wedge of Minkowski space. So this region Rindler space basically lives in that region. Now of course in Rindler space we had a coordinate which had some values, so we had a coordinate x and we said that it's positive, but we could have said that it's both negative and positive. Then we would have got this wedge as well. So now the question is, which one is it? So this illustrates a general principle that if I give you a metric, you can't tell me what the space is globally. First you need to decide what the range of coordinates is and accordingly you will find out what the space is. Okay, so a metric doesn't come with an instruction exactly what space it describes because a metric is local information at each point. Okay, let's try a simple example. What is this the metric of? Sphere. Plane. This is just plain polar coordinates, right? Okay. What's the value of r and theta? Okay. Supposing I feel like, would I change this to 1? What would I get? A sphere.
The region interior to the circle of this one.
Called a disk, right? The region inside the circle. This region is called a disk. Make sure you use correct words. Sphere, circle, disk all sound like the same thing. They are not all the same. Disk. Okay, if I do this. Okay, if I say less than 1, then the boundary points of the disk are not included in the space. If I say less than or equal to 1, then the boundary points of the disk are included in the space. Okay? So, in certain sense, these are all different spaces. If r is less than 1 or less than or equal to 1 or less than infinity, which means it goes all the way up to infinity, they are all different spaces. But some of them are subspaces of other spaces. We can see that the disk is part of the plane, right? Not the whole plane. Now, supposing we try to do something different. Suppose we forgot about r. Let it be its usual values. And supposing theta, we allow it to go from 0 to 4 pi. What do we get? It's an interesting space. It's a very peculiar space because as theta goes from 0 to 2 pi, we cover this plane for fixed r and then we cover it again. So it's like a double cover of the plane. Okay. So there are all kinds of things you can get if you change the range of your coordinates, and some may be sensible, some may not be sensible. Okay. There is no recipe, that's all I am trying to say. Right now I have not given you any exhaustive rules how to deal with different kinds of spaces. You will learn those rules by example. There is no hard and fast thing that, well, if I give you a metric, I know everything about the space. You have to decide the range of coordinates, and depending on what you decide, you will get a space. So then, with Rindler space, with one choice, you get this part of Minkowski space. With a different choice, you get two regions which behave like two copies of Rindler space glued together over here. Just two copies. You be patient, you will see many more examples like that. Okay. Good. Now today, so last time, as you may remember, we looked at a bunch of examples in space-time. We looked at Ringler space-time, we looked at anti-de Sitter space-time and so on. And we tried to get some feeling for how to get geodesics and so on. Some very simple things. And today I'm going to go back. As I told you, we'll keep going back between space, curved space and curved space-time. Okay? Space-time as the key is the key to general relativity, but space is hard enough to understand, and sometimes we want to develop new concepts, then we work with space. So today we are back in space, and throughout from the very first lecture in this course, there's one equation that I keep writing down, and I find it very satisfying that almost anything you need to know ultimately follows from this equation. So this is the geodesic equation. On a space whose coordinates are given as xi, where I goes from 1, 2, 3 up to the whatever is the dimension of the space. If you feel the need for definite space, you can take I to go from 1 to 3. Okay. Now what I am going to do today is to use this as well as some discussion we have had in a previous lecture, not the last one but some lectures back, about the fact that the metric can be made locally identity and its first derivative can be made to vanish by a choice of coordinates, but not its second derivative. Okay? It followed from that discussion that the second derivative of the metric somehow should hold the key to the non-trivial property of space. Okay? Or then, if you by extension, also of space-time. Okay. So we saw this second derivatives of the metric of space or of space-time. So how do we understand this in more detail? Of course, second derivative of the metric is something that I would write Gij_Kl, which is del by del xk, del by del xl, Gij. But of course, this kind of construction is coordinate dependent in the sense if it has this form in one coordinate system, it won't have this form in another coordinate system. This is not a tensor. When we say something is a tensor or not a tensor, we are simply saying that it has the same form in all coordinate systems or it doesn't. And this one is very easy to see that it doesn't, simply by the chain rule. The metric will change by some factors involving del x by del x prime, and then these extra derivatives will differentiate those factors, and you will get something which is not simply the covariant transformation law of a tensor with foreign distance. So today we need to understand how to get around this problem and define it out. So as a preparation for doing that, I'm going to look back at the geodesic equation and rewrite it in a couple of different ways, which will give you some geometric idea of what the equation is telling us. So the equation is d by dt Okay, I've just rewritten the equation. This is the same equation. But I've written it as a differential operator acting on the velocity dx by dt. Okay. What is it? The first term is just ordinary d by dt, and then there's something else, and that something else depends on the metric of the manifold, because gamma depends on the metric. Okay. Good. So I've rewritten it in this way, and I'll give this thing a name. This differential operator I'm going to call d by dt. students who are going to work at some stage or who are already working in theoretical physics should find this interesting, because in every non-trivial dynamical system you end up finding that there is a particular notion of derivative appropriate to that system, whether it's a gauge theory system, a gravity system, or pretty much anything. And this is the natural derivative in that particular kind of system. In this case, the derivative encapsulates not only differentiating along the geodesic, but also adding something as you go along. Okay? So the question is, why is such a thing necessary? Well, first let's give it a name. This I'll call the covariant derivative along the geodesic. Of course, T is the parameter of the geodesic. T is a parameter. So this is a particular kind of derivative. And what it's telling us is that the velocity vector, if I subject it to this derivative, then that thing is 0. That characterizes the geodesic. Okay? So another thing, so the first thing is, of course, you know already, I think we saw this in the first lecture, that d by dt, this is just another way of writing the equation. This is actually, what's the word, covariant under coordinate transformations. But if instead of capital D by dt we had only had the first term, then it would not be covariant under coordinate transformation. So we understand the reason why we need to do this. This is the only meaningful equation you can write that the velocity satisfies to first order in time along the geodesic. And of course, in flat space it reduces to the ordinary derivative along a straight line. Okay. Now, let's generalize this as follows. Instead of the velocity v, consider a general vector field Wi on the space. What is a vector field? Well, it's something that intuitively we all understand. Just imagine a space. As I've told you, if you can't imagine a general space, think of a sphere. Okay? A vector field is just an arrow with some direction and length pasted on this at every point. You can think of it as the instantaneous wind flow pattern on the earth, for example. There's a vector at every point of the earth telling you the direction and magnitude of the wind. Okay, so that's an example of a vector field. Anything like that is a vector field. We'll assume that it's sufficiently smooth, doesn't have any singular behavior and so on. Okay, so I have a vector, 3 vector if you like, in special case, at every point of the space. And Vi itself is an example, but Vi is defined only along a particular geodesic. So along the geodesic, Vi is the tangent vector. So it's the vector which touches the curve, so it's defined along this, but I'm generalizing to a vector field Wi which is defined all over this. Now, let's ask the following question. Consider that vector field Wi and consider a curve which is parameterized by t, and let's try to differentiate that vector field along the curve. Okay, general vector field, but I want to calculate its variation as I go along the curve. The process is very well defined because I want to take the vector field at one place, at the infinitesimally next place, subtract the 2 and divide by dt, small amount. So that's perfectly well defined, and this is the thing. Okay. Now first of all, it's useful to recast this as follows. This is equal to d partial derivative of Wi with respect to xj, since it's defined everywhere, I can take its gradient in xj and then dxj by dt. Just chain rule. But dxj by dt is the velocity vector along the geodesic. So this thing is bj dj wi. Just a way of writing it. Okay. So this describes the variation of the vector field along a geodesic. Now, again, it's quite clear that this is not. Okay, before that, this was for a general vector field. Now imagine that a family of there's a family of geodesics. So here's my space, and here are several different geodesics. Each of them has its velocity vector. Okay, so this family defines a vector field Vi. What is it? On every geodesic, it's the velocity vector on that geodesic. Okay, so if I ask what's the value of the vector field here, then first I construct the velocity vector of this geodesic and then I evaluate it at that point. Okay, is that clear? So Vi is a special example of a general Wi, and so I can also consider, so therefore d, the rate of change of that velocity along the geodesic by the same formula is Vi di, sorry, yeah, is Vj dj di. Okay. Now, where have we seen such a thing before? Consider the first term of your geodesic equation. It's d by dt of Vi. So it's just this term. Okay, so this is the first term of the geodesic equation, from which we see immediately that this term cannot be by itself general coordinate invariant. If I change coordinates because of this derivative acting on V, and if I use the rule for transformation of vectors under coordinate change, this term will not be invariant. In fact, it's the first term in the geodesic equation. So in this language, the geodesic equation itself can be written Vj del j Vi plus, what's the second term? Vj, Vk and gamma ijk. And this gives us another way of writing the geodesic equation, which is Vj of del j delta ik plus gamma ijk equals 0. Okay, just reorganizing terms. And this is reasonable to name Vj dj Vk. So I've rewritten the geodesic equation in a second way, for which I've introduced a quantity called Vj, which is the covariant derivative in xj, and is defined like this. Okay, when acting on a vector field, is the ordinary derivative plus a linear transformation involving derivatives of the method. Okay. So this is also called the covariant derivative. And if you compare it with the one I defined earlier, it's not that different. This one is the projection of this one along Vj. Okay, so this whole operator Vj dj is the operator that I defined here as capital D by dt. Is that clear? Good.
So won't the capital D will contain both all the indices ijk because the expression.
Yes.
Yes, you wrote only Vj, Dj, Vk.
Yeah. Okay. Good. So this is a question that's maybe worth clarifying once. I had written this equals 0 as the geodesic equation.
For all k.
Of course, the equation is true for all k, but that was not the point he was making. His point was that this thing doesn't only depend on, so supposing I fix a component k like 1, then ordinary derivative of v1 depends only on v1. But covariant derivative of v1 doesn't depend only on v1 but also on v2 and v3, because this definition is dj of vk plus gamma k j l dl. So you see this interesting thing that the entire vector participates in this, not just component by component. The ordinary derivative, it participates component by component. Okay, but for example, the covariant derivative of the first component of the vector involves the other components of it. So one could be very pedantic and write dj k l on vl. The covariant derivative is indeed a matrix in that sense, but we don't bother, we just write it this way. It teaches us something, namely that when we are considering spaces and possible coordinate transformations, then the individual components of a vector have no meaning. The whole vector has a meaning. Okay? You know that. For example, a vector pointing in the z direction, there is no special status in life. It's just pointing in the z direction because that's how you defined your z direction. You change your mind about what is the z direction, then the vector is no longer pointing in any particular direction, it's pointing in a generic direction. Okay, so those are things we learned here. Okay. Good. Now, so this is the geodesic equation, and in general, given a curve, not even necessarily a geodesic, Vj, Dj, Vk is well defined. In the sense that transforms as a vector under coordinate transformations. So by the time of the next lecture, I'll give you a homework assignment for those who want to do it, where many of these things will have to be checked. If people who are seeing all this the first time need to check all these results. But the basic reason for it is that the covariant derivative is designed to do that. Okay, another way to say it is you saw that the geodesic equation itself is general coordinate invariant. We saw that in the very first lecture. And the both terms are needed for that to be true. Okay. So this is well defined. So it's a vector with one free index, the other two being contracted. And it's one which vanishes if I'm going along a geodesic. And it doesn't vanish if v is not the velocity vector of a geodesic. But it's well defined. Okay. And on a geodesic, it's 0. And of course, if it's 0 in one coordinate system, then being well defined, it will be 0 in all coordinate systems. So this statement is completely coordinate independent. Okay. And this brings us to a way in which we can define a geodesic in a way that uses words that doesn't use any specific equation. So I'll come to that in a second. In fact, this is also well defined. And also transforms well, where W is any vector field, but V is the velocity vector along a geodesic or along any curve. Okay. Now let's try to interpret what this thing means, okay, compared with something that we know in flat space. Supposing in flat space, I had a vector W. Again, I am considering a vector field. So it's a vector Wi at every point. So let me consider a special case where Wi is evaluated at two neighboring points separated by dx. Okay, so this is Wi of x plus dx. Okay, and the second vector, this if dx is small enough, can be written dxj del j wi. So plus the original. Okay, this is w at x. I'm just making a Taylor expansion to first order. Okay, so here's wi at x, and this is the new value that it takes at x plus dx. So what's the change in w as I go from here to here? It's this much. Okay, it's very similar to the quantity we've been discussing. In fact, if there was a curve such that dx was tangent to that curve, then this change would be the same as vj dj wi times dt. Is that clear? So this quantity can also be thought of in ordinary flat space whenever I am comparing two vectors in points. It actually tells me the difference between them. Okay. Now supposing the vector happens to be one which doesn't change when I go from one point to the next, then of course this quantity is 0. Okay, and this will happen if this vector is transported in such a way that its direction doesn't change when I go to a new point. So it's parallel to itself at the beginning. So this thing can be called, so this equals 0 if and only if wi has been parallel transported. So this is the definition of this new concept. Many of you may have heard of it before. In other words, if a vector in going from one place to a neighboring place is parallel transported, which is the intuitive meaning of this word because we are in ordinary flat space, then this quantity is of course 0. Okay, because then wi at x plus dx is the same as wi at x. Now we want to generalize this concept for a general manifold. But for a general manifold, this combination doesn't make sense because it's not independent of coordinates. Okay, there is something which is independent of coordinates, and it's the thing which we've been discussing for the last 10 minutes. So that leads us to define in a general manifold or in a general space, possibly curved space, wi is said to be parallel transported along a curve xi of t if vj, which is the velocity vector of that curve, times capital Vj wi is 0. It reduces to our intuitive meaning of parallel transport in flat space, but it has the advantage of being well defined in curved space. It's also not such a mysterious operation as this equation might suggest. Let's take an example and see how a vector gets parallel transported before we proceed any further. Here's the example. Two-dimensional sphere. I'm willing to bet that the only space people can actually imagine clearly is a two-dimensional sphere. All other things somehow we do by abstract manipulations. But two-dimensional sphere we can make, we can keep it in our living room and we can admire it, and we can even do parallel transport on it. So here goes. First of all, let me be along the equator. Then let me take this vector like this, which is tangent to this curve. Here it's tangent to the curve like this. Here it's tangent to the curve like that. So you see that from my point of view, standing outside this sphere and looking at it, the vector is sort of turning round. Okay, But of course, it's always the tangent vector to this equator. Okay? So it's being parallel transported to itself as I go along. Okay. That in particular means, since this vector is the tangent vector Vi to the equator, it means that Vj, dj, Vi equals 0. Okay? This I am interpreting as a consequence of the parallel transport equation for the special case where W is the velocity vector. But of course, this is also the geodesic equation itself. Okay. So we've learned that geodesic equation. So geodesic is a curve, any curve whose velocity vector is always parallel transport. Now, it's not only velocity vectors which can be parallel transported. Let's consider the same geodesic but a different vector which is not the velocity vector. Consider a vector pointing like this, located at the equator but pointing upwards. Okay. So now if I parallel transport it, how will it look? Along this, it will always be pointing upwards. Right. So under parallel transport, it will always point towards the North Pole wherever it is on this geodesic. Okay? But now, it's not a property of anything, it's a definition that given the vector here, if I say I want to parallel transport it up to here, then this is the vector I'll end up with. Okay? And how will I do this? I'll take this vector and I'll make an infinitesimal change in it satisfying this equation. Vj dj wi equals 0. For that, I need to know the velocity vector on the geodesic. I also need to know the metric on the sphere. It's not obvious that this is the easiest of equations to solve, but hopefully I can solve it one infinitesimal unit at a time and then integrate that until I find out what I have got at the end of some finite distance. So in principle, it's not a difficult thing to do. Okay. Good. And I'll come back to this example in a moment. So we'll do two more little calculations and then we are ready to define curvature. First of all, given that dj of wk is this, what should be this on the product of, let's say, two different vectors. Let's assume that wk and z are two different vector fields. What should be the covariant derivative of a product of them? Okay, and the answer, of course, is that it's up to us. The covariant derivative in the first place was up to us. It's a convenient quantity to define because some natural equations in geometry and also in physics are expressed in terms of it. Okay, so here also we should define it in terms of convenience, and convenience usually means it has some good properties which are shared with an ordinary derivative. And the most well-known property of an ordinary derivative, if this was an ordinary derivative, then this equation would have certainly been true. This is the distributivity property of the ordinary derivative. Okay. So let's require that the covariant derivative on a product of vectors enjoys the same property. can see that this requirement of course defines it because we know every term on the right side of this equation. We know what's B acting on a single vector. Sorry, I think there was something wrong there. And we know this. So I plug in all the definition and I'll get the definition of this. So let's do it. So the RHS is del J of Wk plus this, that's the first term, plus this plus K gamma L M N. So let's rewrite this. These two terms again add up into the ordinary derivative of the product. So that's still there. And then we have two new terms. One is gamma Kjm Wmzl and the other is gamma Ljm Wk. So let's stare at this and see if we can make a rule out of it. So the covariant derivative on the product is the ordinary derivative on the product plus two terms because the object we are differentiating had two indices K and M. One term for each index in the original object. Okay, and what is that term? Well, pick the first index K and replace it by this combination gamma Kjm Wm, leaving the second index unchanged. And then add another term in which you keep the first index unchanged and do the same treatment to the second index. Very easy to remember. Okay. Now this has two nice consequences. First of all, this definition makes perfect sense also if I didn't start with the product of two vector fields. I started with something else. We just happen to have two upper indices, some, let's say, T, K, L. That tells you the rule for covariant derivative of TKL when TKL is equal to WKZL for two independent vectors W and Z. But you could imagine having some second rank tensor which is not the product of two vectors. Okay? An easy way to find one is to take the product of two vectors and add it to the product of two other vectors. At the end, whatever you got is not the product of two vectors, but it still has two upper indices. Okay? So you can simply define dj on TKL as the ordinary derivative plus a term which acts on the first index plus a term that acts on the second index. Doing answer. Okay. I've simply replaced the pair of vectors there by something which has two indices. Now if I can do this with an object with two indices, I can do it on an object with n indices. I leave that to you to work out. All that it will be is the ordinary derivative of the whole object plus one gamma term for every index in the object, every upper index. Okay? So in this way we have derived, and I hope we have derived in a way that we won't forget. Okay? There's nothing to cram or memorize. You can derive the rule for more and more indices just from starting from the original geodesic equation. The geodesic equation is everything in my way of thinking about this subject. So from that, we essentially come to this. Okay? And the key property, of course, is that if T transforms under general coordinate transformations in a certain way, then this quantity will also transform nicely under general coordinate transformations. Just maybe I'm belaboring the point too much, but let's do one example. So a property of the above definition is that dj prime t prime of kl or x prime is going to be given to be dx m j Okay, what's happening is that under coordinate transformations, t will transform with these two factors, and d, covariant d, will transform with this factor. Okay, and therefore you will get all the three factors. But if I hadn't taken the covariant derivative, if I had dropped these two terms, then this right hand side wouldn't have been true, and so any formula involving this wouldn't have a nice transformation law when I go to new set of coordinates. In particular, if there was some tensor for which the left side was 0, in this case you see that if this is 0, then this is also 0 at the same point, because these are all non-singular matrices. But that wouldn't be true if I hadn't used the covariant derivative. So you can see repeatedly what's the power of the covariant derivative. And I'll just write easily generalized. You can try this exercise yourself. Now we know that tensors come in two types, those with upper indices and those with lower indices. I haven't gone through this in very much detail here. Of course, you can find it in standard books. But so the fundamental way of thinking about this is that dxi by dt, which is a velocity vector, has an upper index, because x itself is assigned an upper index. X being assigned an upper index is the convention that you could have changed, but it's a universal convention. From that follows the fact that b has an upper index. Okay, but it also follows that if I take the gradient del by del xi of a function, which I also sometimes write as this, del I of f, then this has a lower index. You might have come across the notation contravariant vector and covariant vector. I think more modern notation is to just call this a vector and this thing a dual vector. Dual has a fairly precise meaning in mathematics, but we can actually exhibit what's the dual relationship between these two right here, which is that the combination del I of f times vi, where vi is an arbitrary vector field and f is an arbitrary function, which I have differentiated along all possible directions in the space to get del I of f. So this combination, you see, has no free indices. So this is a scalar. And this somehow embodies what dual means in mathematics. It means given a vector, dual is that thing such that when I multiply the two together, I get a scalar. Okay, so that's the whole wording is contravariant, covariant. It's the same thing. Okay. So now we can ask ourselves the question, what is the covariant derivative of a dual vector? E.g., the gradient of a function. Dual vector doesn't have to be the gradient of a function. This is an example of a dual vector, but anything with one lower index is a dual vector. This is just one way to generate examples of it. So let's not take that. Let's just call the dual vector alpha I and ask what should be the covariant derivative. So simple way to answer that is, let's ask the question, what's the covariant derivative of a scalar? Okay. Now here, if you think about it, we haven't actually addressed this, but if f is a scalar function, then the only possible derivative on it is del I of f. There's simply no other way you could add a term in here. If you try, you can try with involving gamma I, j, k or whatever. There's no possible term to add. Moreover, there's no need to add such a term because this thing transforms correctly as a dual vector with the correct factor of del x by del x prime. You don't need to add anything. So for a scalar, the natural derivative on a space is the ordinary derivative. For a vector field with the upper index, it's the covariant derivative we'll be working with. Okay, so now we see how to answer the question, what is the covariant derivative of a dual vector, because we'll make the following requirement. We'll say the dual vector contracted with an ordinary vector wi, this is a scalar. So the derivative on it is the ordinary derivative. Of course, this satisfies that this derivative is the same as del j on this times that plus this times del j on that. But we'll require something stronger, that this is equal to this times wi plus this times. And now you begin to see the beauty of covariant derivatives. The same symbol keeps changing its meaning depending what it acts on. And it organizes itself so that whenever it acts on something which transforms well under coordinate transformations, it gives you back something which also transforms well under coordinate transformations. So you could have as well said that this was the covariant derivative on this scalar. This is the known covariant derivative on vectors which we've been talking about for the last half an hour. And this is an unknown object, but of course I can solve it because I can write that this is equal to that minus that. And I get an answer which is true for arbitrary vectors w. So I can drop w and I'll find the answer for dj on alpha. Okay, so it's very easy to do that, and you'll find that dj on alpha I is, of course, one term must be the ordinary derivative. Remember that there is a limit when the space is flat and the metric is everywhere delta ij, when all derivatives reduce to ordinary derivatives. So then, of course, this equation has no mystery. This is ordinary derivative, so this is also ordinary derivative. So this term must be there. It's the next term which now comes with a minus, and the indices are contracted somewhat differently because alpha has a lower index. So it contracts with an upper index on gamma, and these two indices are the ones of the left hand side, and the minus. The minus sign exactly comes by taking this to the other side of the equation. So this defines the covariant derivative on a dual vector, and now it's no work at all to extend this to the covariant derivative on a product or any number of objects with lower indices, or indeed any object with any number of lower and upper indices. Now we can differentiate anything we like. And geometrically what we are doing is we are performing the only natural differentiation operation on a space where there is a metric which leaves all formulae invariant under changes of coordinates. Now there is a question which we could ask. So now we are in possession of the materials or the tools to ask the question. We want what second derivative on the metric Gij provides the definition of curvature. We are sort of guessing, given all the tools we have, we are trying to ask what is it we should do to extract the thing which has a right to be called curvature and which will tell us the invariant curvature information of a space, not the stuff which can be removed at a point by coordinate transformations, but the stuff that is really intrinsic to the space. So you might guess, here's the metric, it has two lower indices, so it's actually a dual vector twice. It transforms like a product of two dual vectors. So I can perfectly well perform two covariant differentiations on this, and one would think that now I finally got my answer. I've got some tensor which depends on second derivatives of the metric, and hopefully it should encode the curvature of the space. Unfortunately, the guess is wrong, and for a very amusing fact, let's calculate the first covariant derivative of the metric. We have the formula already, so let's do it. It's del L of Gij minus gamma Li m Gmj minus gamma m Okay, this is the first derivative of the metric. Let's stare at the right hand side. What does the right hand side depend on? It depends on the metric. In fact, here's the ordinary first derivative of the metric. What does gamma depend on? Ordinary first derivatives of the metric. With this, I remove that first factor which was there. I hope people remember the definition of gamma, if not look it up. So everything on the right side depends on ordinary first derivatives of the metric. But we know that by a coordinate choice, which we saw a few lectures back, those can all be made zero at a point. Therefore, RHS can be made to vanish at a point by a coordinate transformation. Because with that coordinate transformation, term by term, each of these terms will vanish. All derivatives of the all first derivatives vanish. But now, to our surprise, the left side is a tensor. By definition of the covariant derivative, this thing is a tensor. If something is a tensor and it vanishes in one coordinate frame, then it vanishes in all coordinate frames. It vanishes at that point in all coordinate systems. Being a tensor. That's the whole point of a tensor. Remember, such a statement is not true of each piece in this formula. Each piece in this formula can be made zero in one choice of coordinates, but each piece is not a tensor, so it will be non-zero in some other choice of coordinates. But the whole thing is a tensor because it's equal to that. Now if it's zero in one choice of coordinates, it's zero in all coordinates, and therefore it's zero at every point. It's identically zero. Now, you may not want to buy this argument, and you're not obliged to. You can instead write down the definition of gamma and expand out this expression term by term and add up 3 terms from here, 3 terms from here, and this term, and you'll find that they all add up to 0. So I'm not pulling something mysterious on you, I'm just telling you a simple way to see the same fact, because this will be useful in the future. But if you don't like this way, you can expand that and you'll find that all terms just cancel out. It's just 0. So we learn that the covariant derivative of the matrix is 0. This is a property sometimes called metricity. Now, one thing I am not going to dwell on in this course, but some books do dwell on it, is that there could have been many definitions of the symbol gamma ijk, not only the definition we are working with. We are working with a definition where it's a particular sum of 3 terms, gij, comma, k plus something minus something, half in front and all that. That's a particular definition called the Christoffel symbol. Okay. But some people who work with geometry in a more abstract context use the word affine connection for this, and the affine connection may or may not be equal to the Christoffel symbol. But for me, the affine connection of Christoffel symbol arose because of the geodesic equation, which arose because we started with a particle moving on a manifold or on a space with a metric, and we simply said what's its Euler-Lagrange equation of motion. That gives a unique answer with a unique choice for gamma, which is the Christoffel symbol. Okay. So as far as I am concerned, the only gamma ijk that occurs in this subject is the Christoffel symbol. But if you like, you can talk about more general cases. There's a very good reason why we needn't talk about those more general cases, namely, they differ from this by a tensor, and so we can always add that tensor into the equations of motion by hand if we want as an extraneous effect. We can say, well, it's a particle moving on a space under the influence of some external force. So anyway, if you're not following this discussion, it's not important, but I see some people nodding, so perhaps they were arguing about it or wondering about it. So if so, I just wanted to clarify my attitude that gamma always means the Christoffel symbol for me, and then this statement is true. If gamma had the ability to be other things, then this statement might not be true. Yeah, any questions? Okay, so it seems like this result has rather dampened our idea of taking two derivatives on G, because the first covariant derivative on G is 0 everywhere in this space, so the second covariant derivative is 0 as well. So that's definitely not the definition of curvature. So let's try to do something a little different. And for that, let's go back to our definition of parallel transport and notice some nice thing that we can easily do, unless I get it wrong, on our favorite space, which is the sphere. Now we certainly think that the sphere is curved, although I should say it's not just obvious from looking at it, because you need to be living on it and making measurements to find out that it's curved. But you might know that in the development of non-Euclidean geometry, the idea was, let's draw a triangle on this space and let's add up the angles of the triangle. But what's a triangle? Well, a triangle is something whose three sides are all geodesics. Okay? Then you call it a triangle. That's the correct definition of triangle in ordinary space. So let's draw a triangle where I take a point on the equator, I go directly to the North Pole, and then I come down along a different longitude. So these are both longitudes, so they are geodesics, equator is geodesic, so this is a good triangle. Okay. Now it's well defined what are the angles at each of these, because in the neighborhood of this point you can take the tangent to this geodesic and the tangent to this one. Those are straight lines, and you can measure the angles between them. Okay, and it's a fact that the sum of these three angles is greater than 180 degrees on a sphere, and that shows that the sphere is actually curved. You can cast this fact in the language of parallel transport as follows. Let's take a vector that's originally pointing tangent to this longitude and parallel transport it all the way to the North Pole. Okay, so at the North Pole, it's tangent to this longitude, which is going to go down on the other side. Okay, now let me parallel transport it along this guy. So it's going to be basically, well, something. Okay, and now I parallel transport it back, and when I reach back, I find that it's not pointing in the direction it was pointing before. Notice something about this whole operation. I can't really compare this vector with that vector to say it's parallel, because they are vectors at different places, and I can't compare vectors unless they are at the same place. Okay, in a curved space. In a flat space that's also true, but by habit, if you give me a vector and it happens to be there, I'll drag it over here and then compare it with my vector here. But what am I doing is parallel transport. So saying that this vector is the same as that only means that every step of going from here to here satisfies that equation dj on wi equals 0, the parallel transport equation. But that equation was done along this with the velocity vector v of this geodesic. Then it's done along this with a different velocity vector of the other geodesic, and finally it's done along this with the third velocity vector of this geodesic. And nobody guarantees you that at the end you come back to the same vector, and once you've reached the end, then of course you are free to compare these two vectors. You can actually just compare them, and one is rotated. Of course, the magnitude cannot change because you are doing parallel transport, so its magnitude is always constant throughout. It's only the angle which can change. If you find an angle, then it's reasonable to claim that this represents curvature. Okay? Because in particular, if this was not the sphere but it was flat space and I did whatever I've described here, then I would find no angle at the end. Okay? This is the philosophy. Now there are two ways to describe the actual procedure. So let me do both. Parallel transport along a closed curve gives back a vector which is a rotated version of the original. Okay. How do we parameterize this? Well, a closed curve can be defined. A very simple example of a closed curve is just a square. So it has two directions, basically, I and j, for some fixed I and j. And then after going an infinitesimal amount along I and then along j, I have to come back along I and come back along j. Alright? So when I take a vector w to start with, wk, it's going to turn into itself with some rotation in front of it, some rotation matrix. Okay, that matrix is going to depend on I and j. Okay, and it's also going to depend on. So it has two indices for that, and of course it's a rotation matrix, so it should have two indices as a matrix. So we'll parameterize it by saying that it is R K L I J W L. So this is the linear transformation on the vector that we expect to get after parallel transport, and we'll do a calculation and it will turn out that this quantity R K L I J is in fact dependent on second derivatives of the metric, and it transforms as a tensor. So this will turn out to be the object we are after. Okay. Just to again rerun what these indices mean. Normally the rotate of a vector wk would be RKL rotation matrix looks like that, it's the matrix. But here we have chosen a particular path to do parallel transport around, and there's no guarantee that we'll get the same rotation matrix for every path you choose. After all, consider that sphere. Our path went to the north pole, then came down and came back, but it could have gone along any three lines in a triangle and come back. Okay, and nobody is saying you would get the same rotation on that vector for every possible choice. Okay, in particular, we could have gone through a much shorter path like this, and you'd expect that the rotation is perhaps not so large. Okay, or you could go through a path in some other directions. This is only a two-dimensional sphere. If it was a huge dimensional space, there would be so many ways to orient your path in I and J. So the rotation matrix should be parameterized by two more indices I and J. That's why I expect something of the form R, K, L, I, J. Yes.
So, do we have to change at least more than one geodesic? I mean, if we follow just the equation,
Yeah.
so we have to take at least.
We have to take more than one indeed. And in fact, that's a good question. That also can be understood by the following fact. Consider that a path, it's some kind of loop, right? Now for this loop to be meaningful, I and J should be linearly independent, right? If I and J are the same direction, it isn't a loop at all. Okay? In fact, if you remember your Stokes theorem and all that, which we'll be using now, the vector that we associate to a loop like this is normal to it in the third direction. Okay? And that is constructed in 3 dimensions by taking an antisymmetric combination of I and J. And in fact, it will turn out that this R, K, L, I, J is antisymmetric in I and J. It's the same property as what you said, because if I and J are both the same direction, then an antisymmetric object is 0. Okay.
So what is the motivation of writing I and J as lower indices?
Okay, that you'll see in a moment. At the moment, actually, for this formula, you could actually have thought of I and J as, okay, no, I think I can answer your question. The derivative along I and along J has lower, derivatives have lower. That's really the reason. We'll see that it arises from derivatives. Okay. Good, so we have exactly enough time to do the derivation. And there are exactly 2 ways that I know to do it. So let me first do this. The thing I just said with parallel transport from the closed loop. So let's just assume there's a closed loop. And now let's assume that it's of infinitesimal size. Why? Because otherwise, what does this measure? Supposing I take a very large closed loop and parallel transport the vector and it comes back rotated, and I find this rotation matrix, what do I associate it with? It's a property of some average curvature of that space over some large region. Okay, but I want the curvature at a point. If it's possible, I would like to know the curvature at each point. So of course I can approach that by saying, let me take my loop smaller and smaller, and in some limit, this will be a local object which will depend only on the metric at that point, and its second derivative specifically at that point, but no more. Okay. So that's the motivation to take an infinitesimal loop. And so now what we'll do is that this is my loop now, the space is somewhere, and if I have a vector Wi in the beginning, then after going round, I come back to some new vector W tilde I, and I want to calculate delta Wi, which is Wi tilde minus Wi. Okay. By the way, I got this derivation is in every book on general relativity, but in my opinion, the most elegant and shortest version of it is in the Landau and Lipschitz textbook, Classical Theory of Fields. Whenever you want a short and very clear derivation, that's the place to look. Good. So this, for a loop, can be written as the contour integral of dwi by dt over the loop times dt. Okay. Now we are transporting it around this loop by parallel transport. But parallel transport means the equation Vj Vj Wi equals 0, how we defined it, or another way of saying it is dwi by dt plus gamma ijk dxj by dt wk equals 0. This is the equation of parallel transport. So I am free to take this in this thing and replace it with the minus of the right hand side. So therefore this is equal to minus integral of gamma dxj by dt wk dt. So far so good? Okay. Now this is an integral round a curve, and Stokes' theorem tells us that the integral round a curve is the same as the integral of the curl of the object over the area bounded by the curve. So let me write Stokes' theorem. Integral fi dxi is the same as integral half integral del j fi minus del I f j. This defines curl, and d sigma ij is the area element of the area bounded by the curve. You are more familiar with this in 3 dimensions because of the fact that every area element is uniquely specified by a normal vector. Now in 4 dimensions, for example, that's not true. Why is it true in 3 dimensions? Because d sigma ij, if I contract with the symbol epsilon ijk, converts it to a vector, and that's the normal vector. Okay? In general, an area element is specified by a second rank tensor like this, just specifying the 2 directions which bound that area. If the area is in the xy plane, then I and j will be x and y. Okay, area is always specified by being in a particular plane. So this is Stokes' theorem. Now fi is all this stuff. In fact, it is all the stuff multiplying dxj will be ft. So good. So actually this formula is better written without the dt. Okay, so this can be identified with f. Good. So delta of wi is equal to a half integral del. So there should be a minus sign somewhere. What have I done?
Have a minus from the last equation.
I have a minus sign in the last equation, but my notes don't have a minus sign in this equation. But that could be, let me write the equation and then we'll see whether the sign is right. Does this look right? Actually it is, because you see I have del L and this thing with index M and d sigma L M. So this is the opposite of this, and that's the minus sign. So I have incorporated the minus sign correctly. My great surprise. And this, okay. So this much is clear. Now I use the fact that it's an infinitesimal loop. So I'm going to notice that in here I already have derivatives acting on gamma. So I've got my second derivatives of the metric. Okay. So I can approximate this by the value of this expression at the center of the loop and take out the area of that element outside. So basically I don't do the integral. I just write this for small loops as half delta sigma Lm times some local object, and that object is gamma I M K comma L, that's from this acting on this, minus minus gamma I L K comma M W K. So this is two terms. This is when del L acts on this gamma, or del M acts, del L acts on this gamma and del M acts on this gamma. Right. Okay. There are two more terms when del L acts on W or del M acts on W. So I have to write those terms. Gamma I M K. So far I think I am doing okay. I have just expanded out this into 4 terms. Now notice that the last 2 terms again depend on derivatives of W, and these are derivatives along the directions L and M, which are the directions in which it is being parallel transport. So I can replace del L of W of Wk by minus gamma KLM Wn. Okay, because again I use the parallel transport equation for these 2 terms. So once I do that, you get a half delta sigma Lm, and it's very hard when you're close to a board to work this out from scratch, so I'm writing it out and I'm hoping it will stretch. What happened is del L on Wk was replaced by this, but at the end it was multiplying Wn, but I wanted to pull out a common W from the whole expression, so I renamed some of the indices, and finally I got it in this form. But what you can work this out later, but what you can see by inspection is that 2 terms are derivatives of gamma and 2 terms are bilinears in gamma. Bilinear because there was already gamma del W, and del W got replaced by gamma times W. So the structure of this object is this, and this is defined to be a half R I K L M W K delta sigma L M, and therefore you see that R I K L M is all the stuff in the square brackets. Okay, and it has a name. It's the Riemann curvature density. And in the next lecture, I'll develop some properties of this tensor because we'll need those. But just want to show you some things that are sort of intuitively appealing. First of all, since it has 2 terms that depend on first derivative of gamma, there are going to be terms in that which depend on second derivatives of the metric. That's clear. Okay. Now there will be some coordinate system at a point such that gamma is 0, because first derivatives can be made 0. In that coordinate system, all these terms will go to 0, but these terms cannot go to 0, which means we need not fear that somehow what we have defined is a mistake and Riemann curvature is 0 everywhere. It's not 0 everywhere, and we'll see examples where it's not 0 anywhere. Okay, so at least it satisfies the requirements that it depends on second derivatives of the metric, and incidentally also on first derivatives and the value of the metric at that point. Okay, but that is sort of incidental. The real important dependence is in the second derivatives. So that's one thing. Secondly, we see explicitly from this that it's antisymmetric in LNM because delta sigma LM is the area element of that loop we've gone around. Okay, and if you fix LNM, then it's a simple rotation matrix on WK describing the rotation that the vector undergoes when it comes back from the loop. Okay, and as I said, I think this is an utterly simple derivation. I think as usual you'll see that the only equation that played a role was our friend the geodesic equation in some form. That's actually now relabeled as the parallel transport equation. It's not the geodesic equation anymore. Okay, and that's because geodesics don't actually play a role in this construct. Any closed loop will do. Okay, but that equation dw by dt plus gamma dx dt w equals 0 is all you need to know. And if you're stuck in your dentist's office or wherever, you can use that equation from memory and you'll be able to derive the Riemann curvature tensor. You'll also remember there's a natural half because of this area element having two indices, because you see this contraction takes place twice. LM with LM will be 1, 2 with 1, 2 and 2, 1 with 2, 1, for example. So there's a natural half. And other than that, it's a rotation matrix. So much of the mystery about Riemann curvature tensor, which is how do we remember the formula with so many terms, is sort of solved by this little derivation, which you can do anything. Okay. Now it's certainly true that I have not concentrated on giving you physical situations very much in this course, but I wanted to reach this point, and now we can start to look at physics of general relativity from next time after we sort out all the properties of R. And if all goes well, then next week on Tuesday and also Thursday maybe, and well at least Tuesday, Nitin Nitsure will talk to you about geometry. And the funny thing is, though he's a mathematician, I think he will be drawing, I like equations, but he likes pictures, so you will be getting more pictures from him. Okay, so that will be your entertainment for next, hopefully Tuesday. But this Thursday we'll have a class as usual. Now this Thursday is also the Visurgent day, so Institute will start to go into panic mode around lunchtime. But I'm planning to teach at 4 unless any of you has any problem. Is anybody not, maybe you are not here? Person with the camera. Yeah, you.
Huh?
You are here, you're going to be
No,
here or
actually
not?
I'm concerned with camera. I have come here for camera.
I know, that's why I'm asking you. Will you be here on Thursday with the camera?
Yeah.
Thursday afternoon you'll be here?
Yeah.
Okay. You won't want to go home, need to go home early and all that?
No, that's not.
Okay. Then fine, then I think we are fine at 4 o'clock on Thursday. Okay. I'm sorry, I keep forgetting your name. What is the name again?
My name is Kuntal. Kuntal. K-U-N-T-A-L.
Kuntal.
Yeah.
Where do you stay, Kuntal?
I'm staying in Vashi.
Then how do you plan to go home on Thursday?
Yeah, actually, I'm going home at 8, 9 also. That's
Actually, it doesn't. Trains are generally okay at that day. Yes, sir. Puja time, sorry. So next time, beginning of the lecture, you have to remind me, and we'll have discussion on this. But tell me the dates anyway. Better than that, go back to your now and send me an email. What is exactly your suggestion? Okay. Then what we can do is I can SMS it to the class and have a discussion.
कोई